Hello everybody, this is Mr. Hinnon, and we are going to take a look at kinematics in two dimensions, projectile motion, launched at an angle, but now we're going to find the initial velocity. So in this particular case, we are going to, let's see, I'm going to go after some purple here. This sounds good. We're going to see if we can actually find the initial velocity you launch something. So to do this, we need an example where it's a little bit different. So I'm not going to use our football problem anymore because that was given to us. Instead, what I've got is I have this basketball player. They're going to attempt a half-court shot. So we know how far away from the basket they are. So they are given this 14 meters. That is horizontally, if you were to measure from here to the basket, that is going to be horizontally how far away they are. So this is the 14 meters. Then they're going to say that they launch it at a 53-degree angle. So the velocity of this thing is going like this. This right angle right here is 53 degrees. Now, what I want to find is just called V, or the initial velocity. So I actually want, in this picture, it's labeled as V. I'm going to call it VI. I want that VI. In other words, if you're going to make a basket from here to, say, the trash can, and you want to shoot it, you're going to think about two things. How hard do you have to actually throw it? How much force, how much velocity you need to give it? Now, later on, we'll talk about force. That's the next chapter, but I'll give it to us. So when I look at this, one of the things I have is I have both vertical and horizontal stuff that I have to kind of work with. However, a couple of things you may not realize. X is the obvious one. I know that the X is 14 meters. And I know my horizontal acceleration is 0, so we're going to stick with that. My gravity is 9.8. I'm assuming they're shooting this here on Earth. Here's the one that you might not realize. In this particular problem, I actually have them shooting it here, and the idea is it says they are releasing the ball at the same height as the basket. So in other words, if I were to draw a little dotted line, this is being released here, so it's traveling through the air, and boom, it's going right in. That is actually very important because in this problem, what that means is that your y is actually 0. Does the y have to be 0? No, but for this one, I want to make it a little bit easier. The other thing we know is these times are actually going to be the same. I'm going to slap myself up there. And so now here's how I have to work it. How do I get these kinds of things into the equation to actually work this thing? Well, one of the things I have to realize is those kind of trig type of problems I gave to you earlier are still going to be true. So if I write this like this, Vix is equal to Vi times the cosine of my angle. So I'm going to write that in there, okay? The next thing, VIY is going to be VI times the sine of the angle. We're going to put this onto our equation sheet. So if we haven't gotten this on the equation sheet, we definitely need it there by now. The next thing I'm going to do is I'm going to use some of our other equations. For example, I have X. I would love to do something with X. So X I know is equal to Vx multiplied by t. Well, Vx, Vix, they're all the same. These all equal Vx. So I can plug this in here in place of x, or Vx, sorry. So x is going to equal the Vi times the cosine of my angle times my time. I don't know what Vi is. That's what I'm after. I know what x is. I know the angle. So the angle is 53 degrees. I haven't done anything with it, but I don't know time. But here's the cool part. I usually can find time using my vertical stuff. So that's how I'm going to do it. The equation I'm going to use, since I know that y is equal to 0, is I'm going to go after with that equation. So just kind of bear with me a second. It says that y is equal to this VIY t minus my 1/2 gt squared. I did this a little bit on the last problem. When I was trying to find horizontal displacement, I found time. I used this. So I had this thing landing and launch from the same height. And so if this part is 0, it basically means that this and this part have to equal each other. Then I can actually cancel out one of these t's, and I have a neat little way. But I'm going to do a couple little things. I'm going to actually solve this for time. So I did this before. Time would equal, I would multiply by the 2, so I'd have 2 times my VIY all over G. So this is a great way to kind of find it. Move my right there on front of time. I'm then now going to substitute this in. So this is what VIY is. So I have an equation that looks like this, that time is 2 times your VI times the sine of my angle all over G. Now we didn't do it like this because we found time other ways, but I could actually put this on the equation sheet as well. It's a great way to finding time, assuming that it's launched and lands at the same height. And we're going to do that with some of our earlier problems here. So I'm trying to keep this kind of simple. Well, here's the next step. I'm going to take this ugly looking equation, I'm going to substitute it right in there for time because I'm trying to create a new equation, something that will relate things like velocity and displacements and all that stuff. So this is going to be weird, but we're going to end up with an equation that's actually going to have horizontal stuff and vertical stuff in it. So it's going to have both of them. So now I've got x equals VI times cosine of my angle. And then time is found with this. So it's got 2 times my VI times the sine of the angle all over G. Ta-da! Now I have an equation that has x, how far horizontally something travels, g, the acceleration of gravity, the angle that it's actually taking off at, and the initial velocity. I don't want to leave it like that. There should be a way I can compact it together a little bit. So I'm going to do that. I'm kind of running out of space here. So let's grab a new page. Hey, look at that. I can go right here in the middle if I want. I'm going to go up here by the words projectile motion. So I've got the fact that x, whoops, I didn't want to go forward. Go back. Sorry about that. So I've got the fact that x is equal to VI times the cosine of my angle, and then I have 2 times VI times the sine of the angle all over G. I'm going to set this up so it's actually solved for VI. If I do that, I notice I have a VI here and a VI here, so I multiply them together, I get a VI squared. And I'm going to slowly kind of bring stuff over. So let's bring this G over first. So let's multiply by G. I'm going to write that as GX by G. I'm going to bring this 2 over, so let's divide by a 2. Divide by a 2. Divide by 2's. I know I've got VI squared. So put a little square on this. And then I have cosine theta, sine theta. So I'm going to divide by cosine of theta and the sine of theta. In other words, the two things multiply together. So bye-bye, bye-bye. I'm going to do that over here. They're going to be on the bottom with this 2. So I'm going to end up with G times X over 2 times the cosine of theta times the sine of theta. And that equals VI squared. But wait a second, I don't want VI squared, I just want VI. So I'm going to have to square root this side so I can get rid of that VI, that square on there. Let's see if I can grab that eraser. There it is. There it goes. Bye-bye. Grab my pen again. And ta-da, brand new equation that allows me to find the initial velocity when I just know 2 bits of information, how far it goes horizontally and what angle I'm actually going to launch it at. Now, this only technically works if you're launching and landing at the same height. So if it's going a little bit lower or if it's going higher, it becomes a little more complicated, but we could do it. I just like to do with the basic one. So if I was shooting at that trash can over there and I thought about the angle I'm launching it at, I could figure out about how fast I need to launch it. So I have all this information. I should be able to find VI. So I plug in my numbers, plug in 9.8. In this case, they're shooting at 14 meters. That's how far it is from the half court line to the basket. Over 2 times the cosine of 53 degrees times the sine of 53 degrees. Now, I would treat this as all one thing. So in other words, I would do everything in the denominator down here. I would do everything in the numerator and then kind of divide it. Or if you have a nice little scientific calculator like this, you can actually put it in and it'll work it out. So I'm going to go ahead and do that. Let's see if I can get this set up. So I've got 9.8 times my 14. And then I've got 2 times the cosine of 53 degrees times the sine of 53 degrees. Make sure that you're in degree mode if you haven't been changing that. And then that's what VI squared is. So don't forget you guys square root it, because if I just do the inside, I get 142. That seems way too big. But then if I square root that number, I get 11.9. So they are shooting this, or they need to launch this at about 11.9 meters per second. So that's somewhere around 25 miles per hour. So they're really chucking it. That's basically what we have going on. Great little way of finding this. So I'm going to leave you with this question. Whoops, got to move out of the way. Golf ball is being hit, pitching wedge. So the pitching wedge has a really sharp angle to it. It's going to launch it at 50 degrees. So it's going to get hit it up at 50 degrees. It says that it's going to travel 100 meters. So we're going to have, that's our horizontal displacement. I want you to figure out how fast the golf ball is going to leave the club to actually travel that far. Okay? Put that into the Google form. That's your last little bit. Hope you enjoyed. Stay with us at the Henstitute.